Hi, I'm Alastair from 461 the Barker Redbacks, and today I'm going to be doing a workshop on an introduction to CNC Routers for FRC and FTC teams, explain some of the benefits, explain some of the difference to other CNC manufacturing methods, and explain the best tooling to use. After that, I will talk about how to do some CAM, computer-aided manufacture, programming in Fusion. All right, so let's get into it. A CNC router is a computer numerical controlled machine that can move a rotating spindle to specific locations or coordinates. So it relies on numbers from your CAM program, which is then fed into the computer or controller of the machine to actually move to those specific locations. And it typically moves in X, Y, and Z axes, which means it moves left and right, back and forth, and the spindle can also move up and down as it would need to when, for example, creating a hole in the material. So what can a CNC router do? A CNC router is probably the most versatile machine for FRC robotics use. And it can machine most materials. So plywood, MDF, and hardwood, which you typically maybe use for prototyping, for building a field, and plywood especially for doing bumpers. So it does give you the capacity to work with a large number of different materials. I know previously we have actually received benefit from machining up plywood bumpers. So in 2016, we were able to create a sort of S-shaped bumper that transitioned between two heights. And that would have been something that would be quite difficult to do by hand. You'd have to use a jigsaw or something like that. So that was very useful. Now what we actually do with our bumpers is we still CNC route the bumpers. We put the screw holes in the actual bumper wood when we machine it. We also actually do some little recesses and slots in the plywood, which are very shallow, which still meet inspection requirements, to actually recess the staples in. It's about 1/8 or 1/16, and that actually makes the fabric quite flush. Otherwise, our CNC router is really good for plastics. So, polycarbonate, HDPE, ABS, Delrin, acetal, pretty much every plastic you can think of, it has no problem with. Even cheaper CNC routers like a Shapeoko or something like that will easily do polycarb, HDPE, and other materials. And that can actually be quite valuable. If your machine isn't super rigid, you can, start off by doing it out of wood or doing it out of plastic, and then you can move to the aluminium. And of course, plastic is great for flexible components and parts which need to be quite light. But the main thing for FRC usage is the aluminium sheet capacity of it. So it can cut aluminium sheet, thick plate, as well as aluminium extrusions like square, rectangular tubing like you might do for a West Coast drive. And this capacity to do aluminium sheet and thick plate, as well as extrusions, is something that you really don't get from other machining methods. So it is very versatile. You might think, a CNC router is quite similar to a CNC mill, in which it is. But there are a couple of differences. So the spindle RPM is much higher than a typical CNC mill. So normally, if you're looking at like a Haas or something like that, the spindle will be around 6 to 10 or 12,000 RPM. And with a CNC router, they're typically about 24,000 RPM. And this means that they're better suited for slotting and contour cutting in aluminium. And they're also better suited for using the small diameter tools that are normally used to create the small pockets in FRC gearbox plates, things like that. They also have a larger work envelope. So let's, for example, use the Omeo X8 router, which is popular with FRC teams, as an example. The work area of that is, I think, 550 millimeters by 770 millimeters. So that would already be quite an expensive, very bulky milling machine to get that sort of work area. If you're looking at introductory, Tormac mills, Haas, Super Mini Mill, the work area of those is quite small, which means that they're not very well suited for doing the sort of sheet, plate parts, and belly pans, which FRC teams typically like to do. The other thing is the table on the CNC router doesn't move. So the actual spindle head is moving, similar to like a gantry mill, if you're familiar with those. With a CNC milling machine, the material, the vise is all moving around, and the spindle, which is obviously much larger for a CNC mill, remains constant and remains fixed. This brings up the opportunity to do things like having your material being much larger than your machine work area. So if you only want to get if you've got an Omeo, which can only cut 770 millimeters, or the bed is 1,000 millimeters long, but you want to cut your 4x8 sheets of 1/8 aluminium with minimum effort, you could do 3 cuts. You'll have maybe 8 inches or 10 inches sticking out on each side. And then you can sort of feed that through as you use it. And the advantage of that is you end up using a lot less material, so you reduce wastage. So with the CNC mill, normally the whole point is that you start with your flat bar of aluminium and your little jigger and your vise, and you machine all the extra material away. But with the CNC router, the approach is we're going to get this plate, and we're going to put these parts here, and we're going to cut all those out at the same time. So really it does reduce wastage. And the other thing is the aluminium sheet and plate is generally quite a bit cheaper than aluminium flat bar that you would use on a CNC milling machine. Some downsides. Typically they have much slower travel speeds, and most won't have a automatic tool changer or ATC. Some bigger, more expensive CNC routers do, and those are very popular in manufacturing shops and plastics and aluminium and wood production in carpentry, but not usually for the smaller end machines that would easily be within reach of FRC team's budget. You'd be normally looking at above $20,000 to $30,000 for one of those, and a good one. So, for example, from Axes might be $40,000 or $50,000 for a big machine with a tool changer. A big difference to water jet, laser, or plasma is that you're not restricted to cutting all the way through the material. So I'll show you an example of some parts like that now. So we have this gearbox plate here. And then we have this little recess for a actually standoff to go in. And now that would be quite difficult to do on a water jet or laser cut part. You would actually have to do a second operation for that, but we can do that all in one go on the CNC router. And another example would be this little bearing recess here. So there you go, that little 1/16 recess so that the bearing sits flush. Again, that's something that you couldn't do on a water jet, a plasma, or a laser cutting machine. And if you see here on this part, all the edges are flat. There's no taper. And water jet cutters and lasers, you normally get quite a substantial taper when cutting thicker materials. I'll see if I can show another example of this on a part. Here we have this gear, and you can see that these pockets which are in there. Oh. So of course, if you're trying to reduce weight on a component while maintaining maximum strength, machining only about 2/3 or 3/4 of the way through and leaving a thin skin is really good. Some of you might have seen that when doing isogrid pocketing, things like that. So that's really a capability that you only really get with CNC routers or CNC milling machines. It can cut thick aluminium that a laser or a plasma would really struggle with. So typically, a big laser or a big plasma machine is going to give really poor performance and results after about 6 millimeter or a 1/4 inch thick. But with a CNC router, you can go, up to 3/8, 1/2 inch, or even 1 inch thick, without having any taper, without having any issues. And of course, when you're cutting thicker materials, there are obviously considerations there about chip evacuation, things like that. And you can't always cut as fast with these long tools. But it really does give you a capacity which you can't get with water jet, laser, or other manufacturing methods. Of course, you can get it with CNC milling. And so a CNC router is actually much better than a water jet or a laser or plasma for precision, edges, for bearing holes, etc. And in fact, a CNC router will generally be quite a bit faster at cutting aluminium than a water jet cutter. Obviously, a laser is in sort of a league of its own, but a water jet cutter will not cut as fast in aluminium as a CNC router will. But on the other side, there is way more setup for a CNC router than with a water jet, laser, or plasma. So those are normally just cutting along the line. There's a slight offset you have to set up. But with a CNC router, there's a lot more setup time. So you have to actually rigidly hold the material. That isn't really necessary with a water jet, laser, or plasma, because there's no real force on the material. So you just put the material on the bed and away you go. No, with a CNC router, you have to do clamps, screws, or have a vacuum table, things like that. And also, with a CNC router, it has a bit more involved in it. You've got to do the cam as well for that, which would normally be a lot easier for one of the other methods like a water jet or laser. Because of course, if you're using a 5 millimeter diameter tool or 6 millimeter diameter tool, there's got to be those relevant offsets, and you've got to enter all the depth of cut and things like that. So while it does give you a lot of benefits, there are also downsides. The other thing is it can cut plywood. A laser is not very good for cutting thick plywood, and it will also provide a better finish on plastic than a water jet or laser will. And of course, a plasma can't cut anything which is non-conductive. So how can it be beneficial for your team? So if you don't already have a CAD-focused robot design approach or CAD-focused robot build approach or build season approach, the introduction of a CNC router can really help add a lot of benefit to your team. But of course, you have to have the skills and experience, maybe from some mentors who've used it before, to actually use that to the full potential. But it is a good step to move into going down the approach of CADing and machining the parts, rather than simply sort of cobbling or putting something together from a lot of COTS parts. It provides students with more design options for flexibility. A lot of teams will solely work with parts that they can buy from the normal FRC suppliers, such as gussets or pre-drilled tubing or extrusion, things like that. Making your own parts with CAD and then the CNC router or another manufacturing method really provides you with a lot more options and flexibility, and actually allows your students to go a bit more wide with their creativity and what they can come up with. The major thing is rapid iteration. You can machine and test multiple mechanism versions in a day. You could use wood initially, or you could just, if you can afford it and you have the budget, use aluminium in the final materials for every single prototype. And so you're not relying on sponsors or outsourcing. You can machine, you could do 4 or 5 different intakes in a day. You could do 4 or 5 different shooters in a day. If you've got the manpower, it can be really valuable. A lot of teams, they will come up with a shooter design. They'll send it out to their sponsor, or they'll pay for it to get machined by another company, or they'll get another team to do it. They're not involved in the process. Their students haven't necessarily got all of the learning that they can do from that, but it might take several days for that part to turn around. And in the end, sometimes they might only have 1 or 2 chances to actually get that mechanism right. But with having your own machine, you have the opportunity to iterate so quickly, and if you can use it to its full potential, it really gives your team a big advantage. This is a pretty minor one because the extra material usage and things like that will probably cancel it out. And of course, if you're building more complicated robots, then you're going to be using more of other parts. But it can reduce spending on basic COTS parts like pre-drilled tubing, gussets, bearing plates, things like that. That is fairly minor, but also, of course, rather than having to work around a specific gusset, you can design a gusset which has a bigger radius or a different material, a different hole pattern, which really suits your design better. So it's not just about reducing cost of COTS parts. It's really about providing the ability to customize and giving you a lot more options. So these are some considerations when choosing a CNC router for your team. Obviously, they are potentially, and they can be very dangerous machines. When something is spinning, 400 times a second, when you can put your hand in it if you haven't got appropriate measures in place, when something's moving around with pinch points, when there's swarf or aluminium chips flying around, there is the opportunity to have major safety issues. And of course, if you're importing a machine, like one of the OMEO machines, you'll want to check as well that those are actually compliant with your school or local authority with safety standards, and also things like electrical wiring standards and things like that. So make sure you do your homework regarding that. I can't provide that much input on that, unfortunately. As a general rule, the very low-cost machines like the Shapeoko and ones which have V wheels and belts to drive them are great for wood and great for plastic, but they aren't very suitable for machining aluminium. And also, they tend to not be very accurate either. So if you want to be able to machine aluminium quickly and reliably, you really do want to pick a machine that has, proper linear rails, so that there's not a lot of slop, and something which has a ball screw or rack and pinion, if you can. Obviously, some, reasonable machines, say Velox, will have like a lead screw. But if you can, try to stick to ball screws for the small machines, and for the larger machines like full sheets routers, they'll typically have rack and pinions. Think about work area. If you're an FTC team, you don't need to make parts as big as FRC teams do. So you could use a smaller, cheaper machine. And in some circumstances, a machine which is smaller is actually going to be more rigid because the frame is less likely to deflect. And also, if you're an FRC team and you want to be able to make the field, for example, you want to be able to route out a lot of plywood or polycarbonate to make the actual full-size field elements, then you might want to look at using a 4x8 CNC router or full sheet router. So the OMEO X8 22L is a good option for machining aluminium, but of course it may not meet necessarily standards, so check this. You want to get the USB version rather than the sort of onboard control version. As for these small machines, Mac 3, if you have the computer spare, actually gives you a bit more flexibility, and you won't have as many issues about reliability of controllers and things like that. And it also is a little bit cheaper as well. And these are available directly from the manufacturer. Normally it's a couple of $100 US for shipping, and they ship it directly to you via like DHL or FedEx, something like that. Or I know in the US they are available through Swift Robotics, and I believe they'll be available soon from West Coast Products, but you could contact them about that. If you have the space and a budget, so as I said before, it might be upwards of $30,000 US, a full sheet 4x8 router with a tool changer is pretty much the best manufacturing solution for FRC teams that you can get. Axes is a good option. They have a good controller. The machine's quite reliable. They're up in Canada. But really a big 4x8 CNC router is the best option. It cuts, you know, your plastic, your wood, you can cut your aluminium and plate parts quite quickly. You can do tubing. It's one machine which really gives you probably the best return on investment. If you look at the spend, if you were to spend a similar amount on a milling machine, maybe like a decked out Tormac or a Super Mini Mill or a Haas VF1 or 2, you wouldn't nearly get the same capacity that the CNC router gets. And you might think, oh, you can only cut quite slowly, but no, these big CNC routers, which have really powerful spindles, and the high RPM means you can cut aluminium actually much faster than a Tormac mill would, probably by a factor of 2. You know, some of these machines will have a 4.5 or 6 kilowatt spindle and really rigid construction. And the tool change is really helpful as well, because that means you're not stuck using a 4mm bit to, so you can drill your holes and cut your parts out. You can drill your holes with a 4mm drill, or a 3/16 or 532 drill bit, and then change over to your other cutting tool like a 6mm or a 1/4 inch single flute, which would allow you to cut really fast. Chief Delphi has lots of threads and posts with information on other machine options like Velox, Laguna, etc. I don't really have experience with those. So now I'm going to be doing a quick introduction to router tooling. Typically, different materials all require different tools if you want the best results. Even MDF and plywood would have something different. Plastic and aluminium would have something different. But that is really from like a professional standpoint. So, for example, for FRC purposes, the edge finish on plastics isn't really critical. So tools intended for aluminium will work fine. And you still get a pretty good finish. But you won't get like a mirror finish like you might with the actual proper plastic ones. So, if you can reduce inventory and reduce the number of tools you have to have, it is helpful. So for FRC purposes, I typically just recommend using your normal single flute tools used for aluminium. For plastic, if you want, you could put aside one of the single flute tools, because what does happen is if they do get chipped sometimes. So if you maybe get a brand new one when you do your aluminium, and then you'll get a better edge finish. Larger diameter tools are stronger, right? The shank is thicker, they're more rigid, and they can cut faster and deeper. Smaller diameter tools, such as 1/8 and 4mm, can't cut as fast, but are really good at drilling and boring holes. So they make up for that small reduction of cutting speeds with the ability to actually do everything. So rather than having to get your spanners out if you don't have a tool changer and change over your ER20 collet, being able to do everything with one tool is very valuable, and is especially valuable if you're making parts, one at a time. Say, I want to test out this, I make this intake. Having to change the drill over just for 2 parts, having to change the tool over 2 parts, doesn't really make sense. If you were, for example, doing an entire belly pan, or you sort of designed a lot of robot parts and you set up a nest where you have a lot of different gussets on there, then that would be good to use the larger bits for. So you could change it over then, you drill your holes and then change it over. For thin plastic, you can use a downcut bit. So essentially that puts downwards pressure onto the material and preventing it from lifting and flapping around. So that's a good option if you do a lot of 1/16 and 132 polycarbonate. They're very handy. And those bits, even though they look like they will work for aluminium, I wouldn't recommend it, as they're pretty much just for cutting plastic. And if you do use those bits on aluminium, they will work for a while, but you'll have issues related to like recutting of chips and chip welding because those chips aren't being evacuated. So I'll show you one of those tools now. So this is the normal single flute bit for aluminium, and you can see it has that quite pronounced tip on the top. and that polished edge in there. Now look at the same one, which is the same size as a down cut, and you'll see it essentially doesn't have a tip. So when it's rotating this way, it's actually putting pressure downwards. Whereas if this tool over here, when it's rotating this way, it's actually lifting up. For plywood MDF, there are multiple options which work well, as these materials are quite forgiving. The main thing to look out for when doing this is heat buildup. So if you're running your tools too slow, even though tungsten carbide is quite heat resistant, they will still get hot and eventually they will get blunt. So a compression bit is the best for plywood. It essentially puts pressure up and down on the material, which means you don't have any issues with tear out. And so if you're doing hardwood, this is what you want to use as well. I think you can see that. It puts pressure up on the bottom section, and then on the top, it's putting pressure down to stop the actual plies of the plywood lifting up. And then here is the straight flute I was talking to you about. So it's just like a straight blade, and those aren't going to push chips up or push chips down. They'll just cut sideways. They're a good option for plywood and MDF, and they're economical as well. The compression bits can be quite expensive in relation to the two flute straight cutters. I would recommend that you choose router bits with a cutting length that is not larger than needed. The longer the tool, the more likely it is to break. And this effectively reduces the maximum cutting speeds that you can do. It is very rare to use aluminium thicker than 3/8 or 1/2 inch. So pick tools which have a cutting length of between 12 to 15 millimeters. So that would be something around 1/2 inch. And as I said before, the best router bits for aluminium are single flute upcut bits. So these bits lift chips out of the cut, out of the slot, and they also have a geometry that makes them ideal for drilling and boring holes. Other tools such as 2 or 3 flute bits will not be as good for boring and drilling holes as a single flute bit will be. Something else to consider is the diameter of the tool as well. Obviously, the diameter of a tool affects the strength, but also the length. So even if you have a really wide tool, if it's quite long, there's a lot of stick out, it will still be quite fragile. And it really does reduce your effective cutting speeds. Because think about it, if your tool has increased from 12 millimeters to 24 millimeters cutting length, effectively you have made it about 4 times weaker. So these are all sources for single flute bits. I do run aussieboards.com just out of, I just want to put that out there. But they're also available from Swift Robotics and West Coast Products. West Coast Products also has 5mm bits. And these are all metric options. Obviously, there's other suppliers in the US like Onsrad, like Tools Today. They have bits as well. So just really weigh up what suits with your budget. The tool itself, they do vary in quality, but as long as you're running a single flute bit which is intended for aluminium and that it's a suitable length and suitable diameter, you are generally going to have a good experience. All right, so CNC machines require CAM instructions to operate. This is usually in the form of a G-code to tell the machine where to go and what to do. CAM forms part of the bridge between the CNC model of your robot part, between the 3D model of your robot part and the CNC router itself. Obviously, there is a computer inside the CNC router, and so for smaller machines, that'll be like Mac 3 or like Ease or something like that, which does actually take the G-code and feed it to the machine. But the CAM is what you do to turn your 3D model into something usable by the machine, into a G-code. There are multiple options available. Today I'm going to be talking about Fusion 360, as it has a good built-in CAM or manufacturing tab, and it is free for academic and educational use. There's also Mastercam and sort of like SolidWorks, HSM Works, which are also available. And again, Fusion, HSM Works, and Mastercam are very powerful softwares because they're really intended to be used for CNC milling applications as well, not just for 2D stuff. And there are also a range of other options such as nRoute, Vectric, Cut Pro, which are actually very well suited for CNC routers, but they do have a different workflow. These softwares normally stay in 2D. So if you're having trouble with your Fusion workflow, or if you've got a, say like a 4x8 router or something like that, it might be worth looking at one of these other options like nRoute and Vectric. I know Vectric's probably the most affordable one. nRoute's quite expensive because if you're doing wood and things like that, it can be actually much faster, but you're using like a DXF workflow. You're not individually selecting holes and circles and edges. And while Fusion is very powerful, sometimes that isn't needed, especially if you're doing prototyping and a lot of 2D parts. So I just opened this part up in Fusion 360. This is a basic bearing plate. It has a bearing hole to fit a 1/2-inch hex bearing. It has some holes which I think are 532 or 4mm, and it has an outside. So I'll show you the basic steps which you would go through to actually make this part and do the CAM for it. So I opened this file up as a step file as it was imported probably from SolidWorks, something like that. So if you're using SolidWorks, you would just go File, Save As, Step. If you're doing Onshape, you'll do the same. You'd say File, Save As, Step, and then you just open it up in Fusion 360, save it, and then you can start doing your CAM. So what we're going to do is we're going to click this tab here, and we don't want to use Design. We could use Design if we wanted to modify this part. And another advantage of using Fusion for CAM is that you could actually modify this. So as long as my origin stays the same, if I am doing a belly pan or something and I've realized I'm missing some holes, because Fusion is a CAD program, I could actually edit that straight in Fusion without risking the origin point moving, things like that. So we're going to click Design and change to Manufacture. And as you can see here, this is the manufacturing workspace. And this generates toolpath strategies for the design to be fabricated. So let's click Manufacture. And now our menu has changed. So the first thing you need to do is you need to create a new setup. So let's click Setup or New Setup. So I typically just use from Solid, but if you're starting with a piece of like flat bar or something and you want to remove the extra material, then you'd want to actually enter your stock size. But I use from Solid, pretty straightforward, and just select the part, click the part, and it gives us some dimensions here. And in this other menu, we could actually change the origin location. I'm just going to leave that as is. The thing you want to be careful of is that your Z axis is up. You want that pointing up. So that's going to be where your tool or your spindle is coming from. So we can go OK. And now we're going to click 2D contour. Let's up this one here. And the first thing we're going to do is we're going to click this bearing hole. What's important when doing CAM in Fusion is that we have the steps in the right order. You can arrange them afterwards, But what we don't want to happen is you don't want to end up cutting the outside of your part before you've cut your bearing hole or before you've drilled your holes. Because unless you've got really good work holding, that's going to lead to a lot of inaccuracy. So first step is we've clicked 2D contour, and we're going to select this contour here. We want to click the bottom, and now we click tool and select tool. So this is where you need to enter the tool size and the parameters, but then you can actually save this to your library. You can sort of export libraries and things like that, or download other people's libraries, but I find that it's pretty straightforward to just be able to enter the things in myself. So let's click select, and I already have quite a few tools in here, but for the purposes of this demonstration, I'm just going to click library and probably go new tool if I can. New tool, flat end mill. Let's go full screen, and let's call it 4mm single flute. And the cutter diameter, we're going to change that to 1 flute. We don't really need to do this, it's not necessary, but it does help. Carbide. And then this is the important bit. We're going to make sure that these numbers, specifically the diameter, is correct. The flute length and the holder doesn't really matter. It would only come into play if you were doing materials which were thicker than your actual tool, in which case Fusion would actually stop you from doing that, give you a warning. And it's also a good thing if you're doing quite complicated things to see if there's enough clearance for your tool holder and things like that. For now, let's just go 4mm flute length. Yeah, that's like 12mm. But again, that's not really critical. And the important thing is cutting data. Spindle speed. Let's go back to the PowerPoint. These are the two sizes of tool I like to use, 4mm and 6mm. So for 4mm and for small tools, you generally want to start or use basically the maximum RPM you can. So for the Omeo machine or other machines, it's normally about 24,000 RPM. And then starting at around 1,500 millimeters a minute, which is 60 inches per minute, and then about 1mm depth of cut. For 6mm tools, start around 18,000 RPM, 2,000 millimeters a minute, or 80 inches per minute, and 1.5mm depth of cut. But these are all variable, unfortunately. You can go faster than this, and you can cut deeper and faster, but you do need a misting system. Like a mist cooling system, which provides compressed air to clear the chips and also lubricates the tool. So send me an email, here's my email, and I can help you with recommendations for your specific machine and tooling. So here we are back again. So I'm going to enter 24,000 RPM in here. And so it's helpful to add this in here because otherwise we'll end up having to change it all manually later. And the ramp spindle speed, you want to be that speed as well. Cutting feed rate, 1500. Lead and feed rate, 1500. And plunge feed rate, yeah, you can leave that the same. Post-processor, if you had a machine with a tool changer, like an ADC router, then you'll need to actually number each of your tools specifically, so that the machine actually knows which one to get next. But for now, you can just leave it tool 1, and you can also change that in a G-code editor as well. So let's click accept, select. So now I have this tool. It's all shown up with the spindle speed and the feed rate that I added. And the contour is selected as I want. So now we would go passes and multiple depths, and we can just enter this as 1mm. If you are doing a shape with say a very large circle, like an arc or something like that, you would need to think about using smoothing, which, as you can see here, basically removes excessive points and arcs and helps the machine go around. If typically running like Mach 3, this isn't an issue, but sometimes some machines can have, if they've got an onboard computer, the computer itself isn't very powerful, and it can have issues trying to go to each of those coordinates. So now we click OK. As you can see here, it's going to do, this material is 2.3 millimeters thick. I think it's 1/10 of an inch thick or something like that. And so it needs to do 3 passes to actually go down to the bottom. It's going to do, because I've entered that maximum in this 1 millimeter step down, it's going to do 1 millimeter, 1 millimeter, and then like 0.3 of a millimeter after that. And so now if we click simulate, we can actually see what's going to happen here. So we see it comes in, goes down, and then it's slightly off the material to lead in, and then actually goes in to do the cutting. So as you can see with the simulation, it goes around 3 times. And this simulation tool is actually a good way of seeing what our G-code and our CAM is going to do. It is really quite handy. So now we're going to click close. So now we have our first toolpath, this part. Another thing is, if we were worried that our bearing wouldn't fit in here, because if I click inspect, and this is 28.575, which is pretty close to the actual bearing size, that would probably be like a press fit. We could click edit, and we could actually go stock to leave, and we could actually tell it to take away a little bit more. So you could tell it to take away like minus 0.05 or 0.25. But a big thing with this is you really want to be careful what you're typing in. If you miss a 0 or something like that, obviously your part's going to come out the wrong side, or your bearing cord really loose, something like that, and you might not notice until it's finished. So what we could do is we could actually cut this part. If we weren't happy with it because our origin's right in the middle, we could cut the circle. We could come back to our CAM, add some extra stock to leave, or subtract some more material and run it again, and it would just take off a little wafer. And so we could actually dial in the fit of a bearing by running and modifying the CAM a few times before we actually cut the outside. So that's good. Let's go OK. And as you can see, it regenerates it. So now we're going to drill these holes. If I measure these holes, these are 4.1 millimeters in diameter. We have 2 options on how we could make these holes. We could do a 2D bore, but considering that our tool is 4 millimeter and this hole is 4.14 millimeter, you can see that it's going to try to like do a little helix down, right? If we wanted our hole to be exactly 4 millimeter, which would be equivalent to 532, we could go drilling, drill. We could select our 4 millimeter end mill, click this, and then we just decrease our plunge feed rate to about 100, or if you're new to this, 50. That's pretty gentle and has less likely to damage your tools if the material isn't held well. Then you'd click drill through bottom, and we click OK. And so now for this one, if we click simulate again, it's just going to go straight down into this hole and come back up. And so that's quite a nice thing about good carbide single flute tools, especially 4 millimeter, is that you really have a lot of options. You know, I can literally drill with this tool rather than changing it. And drilling with the tools actually sometimes provides much better results than a drill bit. A high-speed steel drill bit, especially a long one, will tend to sort of bend and flex as it goes in, so it might not be straight. And so the hole will become a little bit bigger, or it might wander a little bit. But with a carbide tool, the tools are short. They don't deflect at all. You definitely can't drill as fast using an end mill as you can with a drill bit, because the tip will be slightly more fragile. But the hole finish and the accuracy that you get will be a lot better. I do like to bore when I'm doing my holes. So if you, for example, doing a 3/16 or a 5mm hole with a 4mm, it's perfect. So let's just watch closely what happens when we do simulate on this hole. So sort of see it rotates around. So it's trying to use the side of the tool to actually remove material rather than just going straight down. And that's especially obvious on larger holes. So if we're doing boring or drilling, what we can do is we can right click, we can say edit, and then we can say select same diameter. And so if we have a plate or a gusset with a lot of holes, we don't need to go through and individually select all those holes. We can use select the same diameter and it will drill any holes the same diameter with this tool. In fact, it will even drill the hole we already had selected here. So this one will get drilled twice. But what you could also do is you could deselect this specific one. So if we watch now what we've got now, we're gonna do simulate. Gonna cut that bearing hole. And now it's drilling all of those holes. So now the only thing left to do is to cut the outside of this part. So we're going to click 2D contour again. We can click contour selection. Check that our numbers are still right. Something seems to have happened here. That's okay. I can just retype these in. But normally when you bring it up, they will all be the same. And plunge feed rate, let's move it back up to 300 millimeters per minute. Passes, we're going to go again down to multiple depths. Make sure 1mm selection go okay. I typically like to hold my parts with screws. So I would drill first, put a few screws in, and then cut the bearing hole or cut the outside. The other option is you can do tabs. We could right click. We could right click and edit and add some tabs. And these will hold the part when it's being cut, and once it's done, you can cut these. I like to use a chisel and a hammer. You can use like a multi-tool, things like that. But a chisel and a mallet, a sharp chisel, actually works quite well. So you would need to find a suitable tab width. This is something you should play around with, and it depends on your machine setup, depending on the width that you need. But this is a way that you can hold the parts and that you can do work holding without needing to use screws. And so now if you watch the entire thing, we can see what's happening. So it is quite easy to get your head around it, and there are also other resources available, such as on YouTube, which are quite good. But for some of the things I might show you, for example, if you're looking at like NYC CNC, that might be a bit more complicated than you actually need it to be. This is really simple. And so now that we've done our CAM, all we have to do is go actions, post-process. So if you've got an OMIO, if you had an OMIO, you would just select Mac 3 mil. You'd select CNC Router parts Mac 3 mil, and there's lots of options for that. I've just got another one selected for the machine that I normally use, so I can't easily change that. But yeah, when you first get Fusion as you start using it, just select CNC Router parts Mac 3 mil. You'd go post-process, save it somewhere, and now a editor will pop up. So now I'll just finish off with some more tool and feed and speed specific information. Firstly, it's really important to keep tools within a specific chip load or cut per tooth rotations, which basically is the size of the chip that's being produced. If you don't, you can end up with chip welding or the tool gumming up from getting too hot, and this will normally result in the tool failing or snapping, or it will mean that your edge finish is very poor or that you get quite a big burr. Another thing is feed rates are a bit of a paradox. So decreasing the feed rate, if you're having issues like chip welding or tool gumming up, or a lot of bad finish being produced, decreasing the feed rate can and will, in many circumstances, actually make things worse. So it is a bit paradoxical. You might think, oh, this is happening, I'll just go slower and I'll fix it. But no, in some cases, the problem can be that you're going too slow. Next, depth of cut. Depth of cut depends on machine rigidity. If your machine isn't very rigid, it means the structure isn't very strong. If it has slop, things like that, or that the spindle isn't very powerful, you can still use the feed and speeds that I showed earlier, and the ones which manufacturers recommend. But you just need to go with a lower depth of cut. Something to think about is that good carbide tools, such as the ones listed previously, don't really wear out. So many people will want to use the entire tool, maybe try to cut the material all at once. But realistically, you're not going to break tools. You're not going to have tools fail because they're worn. Typically, you'll have tools fail because they're broken. So that will be the tip has snapped off, or you hit a screw, or your material moves around and the tool snaps, things like that, or your depth of cut is too high in going into a corner, things like that. So don't worry about trying to spread the wear out over the entire tool. In most cases, especially in an FRC and educational circumstance, you will break the tool before it wears out. And it's not that you're going to be breaking loads of tools. A few 5 to 10 tools will be, or even 5 tools will be enough for an entire season. We've made 2 robots worth of parts with 3 of the Aussie board 6mm end mills, and so they are quite good and they do last long in that regard. But typically when tools fail, it's because they break. It's because your material moves around and you get vibration and your work holding's poor. The time when you can do quite a high depth of cut is when you're pocketing. So say you have this bearing plate, right, and you've got these pockets. What I like to do is I like to actually just go in with a 6mm tool and just remove all of that material. So you might need to go around a few times, but you'll start in the middle, you'll go around, you just go out until all that material is gone. And then I like to do one final pass in the precision bearing holes and actually skim off a tiny bit, and that produces a really good finish. So now I'll just finish off the workshop. I don't think I'm going to have time to, unfortunately, show the process to Mach 3 and the CNC routing today, but I might do a follow-up video, which I might link on the Stuy Splash YouTube video. But I'll just keep showing off some other parts. So one thing that you can do really nicely with the CNC router is you can produce gears. Although this is quite a good one for a waterjet as well. But you can see here we have this nice gear profile. This was done with a 1/8 single flute end mill, and this one as well. And this actually meshes quite nicely on here. And if you're using a 1/8 or a 4mm end mill, you can actually make VexPro a bore for VexPro Thunderhex shaft, which is quite neat. Here's another gear. This one has sharp corners on the hex as well as hex broached. But this was done with a 4mm end mill. It's quite a nice gear, very robust. If I recall, this was used for the arm on our 2018 robot, which lifted up, and this was quite reliable. And here's some more gearbox plates. This is an elevator bracket from one of our previous year's robots. This has a standoff on either side, and then they're recessed in there, so that stops. So that's a 1/2-inch hole in there with a piece of, I think it was Vex Pro tube axle stock, and having that little recess in there reduces slop and reduces movement, so it really locks those bearing in tight and stops having a lot of slop and wobble in the elevator. Here's an example of a polycarb part. This is actually reused from the 2016 Cheval de Frise polycarbonate. This is 1/2-inch thick, and so this is done on CNC Router. That's a really nice part. It's nice being able to do the thick polycarb as well. They're really quite robust. And finally, here is an example of some aluminium tubing which has been machined. So you can see we've got a nice weight reduction pattern in the side and all the sides actually. And this is quite easy to do on a CNC router once you have a setup to do it. You just simply do each side at once. It's quite nice, and it's a good way to take weight out of tubing. Some people will say, oh, it's good to use 1/16 wall tubing on thinner tubing. But I and we quite like using, for a chassis, quite like using thicker tubing. And then, you can have your bearing holes in your 1/8, or I think this is 3mm wall tubing. You can have your bearing holes in your 1/8, because that produces a really strong crush-resistant tubing. It does still end up a bit heavier than 1/16, and obviously it's a lot of extra machining time. But on those critical mounting holes, on these bolt holes, such as this one here, and if you had a bearing hole, it is a lot more robust than the thinner tubing. So a pocketed tubing done on a CNC router is really quite nice. So I think I'll finish there. Thanks for everyone who comes and watches this video. I know it's pre-recorded. My email was in one of the other slides, but alastairpilley@gmail.com. Feel free to send me an email. I'm happy to help you out with any CNC router or tooling or cam-related things. Really pleased to have as many FRC teams as I can start and realize the potential of CNC routers, because it really is something that has allowed our team to excel in the last few years. And I think it's something else a lot of other teams can benefit from. And I have worked with a lot of other teams as well who don't have the same resource. And so it really is valuable being able to introduce the CAD and the CNC processes into your workflow. All right, thanks everyone.